All right, buckle up, folks, because today we're diving into some seriously cool science. We're talking about turning pollution into fuel.
Sounds like something out of a movie, right?
I know, but this is real deal, cutting-edge research published just a few weeks ago.
And it's incredible what they've achieved. We're talking about taking something we consider waste, like CO2.
A stuff we're trying to get rid of.
Exactly. And turning it into something we actually need, like methanol.
Which is super useful. You can use methanol for so many things, from making plastics to powering cars.
It's a really versatile chemical.
Okay, so full disclosure, the title of the research paper is a mouthful.
I tried to read it out loud, and I think I twisted my tongue.
Right. But here's the gist. Scientists have basically built this tiny nanomachine that can transform CO2 into methanol, and it's way more efficient than anything we've seen before.
Which is a big deal because,
Yeah.
honestly, converting CO2 into something useful is tough. It's not like those molecules just rearrange themselves willingly.
It's like trying to put toothpaste back in the tube, right?
Perfect analogy.
Yeah.
It's a real challenge to make those CO2 molecules break apart and reassemble the way we want them to.
And that's where this whole single atom catalysis thing comes in, right? It's like giving each copper atom its own tiny toolkit to grab onto a CO2 molecule and force it to change.
It's fascinating. Instead of using big chunks of metal, they're using these special copper atoms called CuSAs, and it's all about how reactive those single atoms are. Each one becomes this super specialized tool designed to break apart CO2 and rearrange it into methanol.
So it's like each atom is a tiny chef with its own set of knives and pans ready to whip up some molecular methanol.
I like that analogy. And every good chef needs a well-equipped kitchen, right? That's where this special material comes in a metal organic framework, or MOF for short.
Ah, yes, MOFs. I've heard of these. They're like molecular scaffolding with all these perfectly sized spaces to hold things.
Precisely. Think of it as a molecular sponge with tiny pores perfectly designed to trap the copper atoms and their partner in crime, something called polymeric carbon nitride, or PCN.
PCN. Okay, now you're just throwing acronyms at me. What is that?
Think of it as the special coating on the chef's knives, helping those copper atoms hold onto the CO2 molecules long enough to do their magic.
So it's all about teamwork, even at the atomic level. Okay, I'm following. We've got our copper atoms, our PCN, and our MOF scaffolding. But how do they actually build this incredible contraption? It's like molecular Lego.
It's even more intricate than that. Imagine building a ship in a bottle, but on an atomic scale. They start with the MOF, which already has those tiny pores we talked about. But here's the really clever part. They create tiny defects in the MOF structure, like leaving intentional gaps in the scaffolding.
Okay, so they're not just using the MOF as is, they're customizing it. Clever, but why? What's the purpose of making those gaps?
Think of it as making room for the good stuff. They use those gaps to sneak in the copper atoms and something called a precursor for the PCN.
A precursor, so not the actual PCN.
Exactly. It's like a blueprint for the PCN. This precursor gets baked at a specific temperature, and that's when it transforms into the final PCN.
And all of this is happening inside the MOF, right? It's like they're baking this molecular cake in a fancy mold.
A perfectly accurate analogy. And the result of all this delicate construction is a truly remarkable structure. You've got your copper atoms precisely anchored to the PCN, all neatly contained within those MOF pores.
It's like they've created this perfectly ordered nano world. But why go through all that trouble? Why is this specific combination material so special?
That's the real beauty of this research. It's not just about the individual components. It's about how they work together. They've created this one-two punch when it comes to CO2 conversion, combining single-atom catalysis with something called heterojunction photocatalysis.
Okay, hold on. You lost me. Let's break that down. We already talked about those hardworking copper atoms and their tiny toolkits. But what about this heterojunction photocatalysis? What's that all about?
That's where the real teamwork comes in. See, the MOF and the UUSAs at PCN, that's the copper atoms, with their PCN coating, they don't just do their own thing. They come together to form what's called a type 2 heterojunction.
Okay, so it's not enough to just have all the right players on the field. They have to work together in a specific formation.
Exactly. And this particular formation, this type 2 heterojunction, is what makes this whole thing so efficient. It's basically like a tiny solar panel at the molecular level.
Wait, are you telling me they're using sunlight to power this reaction?
You got it. The heterojunction captures light energy and uses it to power the reaction, keeping those electrons flowing.
So they're using light to rearrange the molecular building blocks of CO2. That's incredible. No wonder this system is so much better at converting CO2 to methanol.
Right. It's all about efficiency. And the results speak for themselves. This new system is 83 times more effective at converting CO2 to methanol than just using the MOF alone.
83 times. That's like exponentially better.
It's a huge difference. And
Oh.
even compared to just using the CuSAs and PCN together, this new system with the MOF is 12 times more effective.
Wow, that's amazing. It really shows how bringing the right components together in the right way can make a huge difference, but how do they know it actually works this way? I mean, we're talking about things happening at the atomic level. How do they even see what's going on?
Well, that's where things get really interesting.
All right, deep divers, welcome back. Before the break, things were getting pretty microscopic around here.
We were down to atoms, weren't we?
We were. Specifically, those copper atom chefs we're so fond of. They're working away in their fancy MOF kitchens, whipping up methanol from CO2, and apparently it's crazy efficient.
Crazy efficient, yes. But of course, in science, we can't just say, trust us, it works. We need proof.
Exactly, and that's what I love about this research. They didn't just assume, they showed us, and I mean literally, that this process works. We were left hanging before the break, though.
On the edge of your seats.
You could say that again. You were about to tell us how they actually see this reaction happening, like in real time at the atomic level. It's mind-blowing.
It's pretty incredible. So one of the tools they used is called X-ray photoelectron spectroscopy. XPS for short, thankfully.
XPS, got it, because I was not going to try that whole thing again. But fancy name aside, what does it actually do?
It's all about those copper atoms, remember. XPS allows them to analyze what's happening with the copper, like what's its chemical state, as the reaction is going on.
So it's like they've got tiny cameras trained on those copper atom chefs, seeing if they're actually working or just slacking off in the kitchen.
Exactly. And here's the thing. Those copper atoms, they weren't just sitting there. They found that the copper was changing its oxidation state during the reaction.
Okay, oxidation state. You're going to have to break that one down for me. I'm picturing rust or something, but I'm guessing that's not what you mean.
Not quite. Think of it like this. Those copper atoms, they're gaining and losing electrons as they interact with the CO2 and other molecules involved.
Ah, so it's less about rust and more about energy. Electrons are energy, right?
Exactly. It's all about energy flow. The copper atoms are like those little relay racers passing those electrons back and forth, and that's what keeps the whole reaction going.
So it's less about the copper atom itself changing and more about it facilitating this energy handoff.
Exactly. It's this constant give and take that allows the copper atoms to do their job and guide the transformation of CO2 into methanol step by step.
Okay, so those little copper atoms are more like choreographers than just tools, making sure all the molecules are in the right place at the right time. But how do they actually know that?
That's where the real fun begins. They didn't just observe it. They dug deeper, using something called theoretical calculations to simulate the entire reaction.
Wait, back up. Simulations, like computer model.
Exactly. They basically built a virtual reality version of this entire process.
Get out of here. They can do that.
Oh, yeah. And it's incredible. By watching this virtual reaction, they can zoom in on any moment, any interaction, and measure things like the energy changes happening at each step.
So they created a whole molecular movie, and they can pause it, rewind it, and basically see the whole dance routine of the CO2 becoming methanol.
You've got it. And this is where it gets really cool. These simulations confirmed that it's those copper atoms that make this whole thing work so well. And I mean really well.
Like even better than we thought before.
Even better. See, in chemistry, there's something called an energy barrier. You can think of it as the amount of energy you need to get a reaction going.
Like the energy it takes to get a pot of water boiling.
Exactly. What the copper atoms do is lower that barrier so the whole reaction happens more easily, using less energy overall.
Oh, so they're like those fancy, energy-efficient appliances. Same great results, but without the huge energy bill. But how do you measure an energy barrier? It sounds kind of abstract.
Well, they used another really neat technique for that.
Welcome back to the deep dive. We are nearing the summit of this incredible scientific mountain we've been climbing.
We've certainly explored some tiny but mighty territory.
We have, from copper atom chefs to molecular movies, and let's not forget those super sleuthing simulations. But now for the view from the top, what does it all mean? How does this discovery actually translate into the real world?
That's what makes this research so exciting. It's not just a cool lab experiment. It has the potential to change how we deal with climate change in a big way.
Okay. I'm intrigued. How so?
Well, right now, we think of factories as these big polluters, right?
Yeah.
Spewing out CO2. What if we could change that?
You mean, what if factories could actually become part of the solution?
Exactly. Instead of releasing CO2, imagine if they could capture it and use this new technology to turn it into methanol.
A complete 180. So instead of being a burden, CO2 becomes a valuable resource. That's incredible.
A total game changer. And the best part, methanol itself is incredibly useful. We're talking fuels, plastics, even pharmaceuticals.
Wait, hold on. So you're saying that one day my sunglasses, my water bottle, they could all be made from recycled CO2. That's amazing. Sign me up.
It's a real possibility. It's about moving away from fossil fuels and embracing a more circular economy, where we're constantly finding ways to reuse and recycle.
So we reduce pollution, create valuable products, and move away from fossil fuels. It's like hitting a sustainability hat trick.
Right.
But there's more to it than that, right? You said this research has implications beyond just CO2.
Absolutely. It's not just about one molecule. It's about a whole new approach to chemistry. We're talking about manipulating matter with incredible precision at the atomic level.
So it's like this research has unlocked a secret door in chemistry, leading to a whole new set of tools.
That's a great way to put it. These tools, like single-atom catalysis and heterojunction photocatalysis, they have so much potential for tackling other challenges too.
Like what? Give me an example.
Well, what about fertilizer? Did you know that producing fertilizer is a huge energy drain and a major polluter?
I did not know that.
It's true. But imagine if we could use similar techniques to what we've been discussing to create fertilizer directly from nitrogen in the air.
That would be incredible. Talk about a game changer.
Right. Or think about cleaning up polluted water sources, or capturing other harmful greenhouse gases. This research opens up a world of possibilities.
It's amazing to think that these tiny atoms could hold the key to solving some of the biggest challenges facing our planet.
It really is remarkable. But at the end of the day, it all comes down to human ingenuity, doesn't it? Our ability to ask questions, to explore, to push the boundaries of what we think is possible.
That's what I find so inspiring about science. It's about understanding how the world works and then using that knowledge to make it better. And sometimes the most groundbreaking discoveries come from the tiniest places. So as we wrap up this incredible deep dive, what's the one thing you want our listeners to take away from all of this?
That's easy. Never underestimate the power of curiosity. Because asking, what if, is where it all begins. Who knows what incredible discoveries are just around the corner, waiting for us to uncover them.
Wonderfully said. Well, on that note, we'll wrap things up here on the deep dive. A huge thank you to our amazing expert for joining us today and for taking us on this incredible journey into the world of cutting-edge chemistry.
The pleasure was all mine.
And to everyone listening, thank you for joining us on the deep dive. Until next time, keep those questions coming and never stop exploring the world around you.